Question number 31. A playground merry-go-round is at rest, pivoted with a frictionless axis. A child of mass m runs along a path tangential to the rim with a speed v and jumps onto the merry-go-round. If r is the radius of the merry-go-round and I is its moment of inertia, then the angular velocity of the merry-go-round and the child is. Now, the problem can be depicted like this. Let us say this is the merry-go-round. Let the radius of the merry-go-round be r. Now, a child is coming tangential with a velocity v. The mass of the child is m. So, actually the radius of the path in which the child is running is r. So, using conservation of angular momentum, we can say the net angular momentum before the boy or the kid jumping into the merry-go-round is m v r. So this is the angular momentum before the kid jumping into that. After the jumping, the merry-go-round is moving with an angular velocity omega. Now, because the merry-go-round is moving, the angular momentum of the merry-go-round is I omega, and the angular momentum of the kid is going to be m r square omega. So you see, we are representing, because v is equal to r omega, we are using this relation. So these are all angular momentum. So angular momentum is m v r, or we can say m r omega square, or we can say it is I omega. So using that relation only we are using here. So we want to find what is the angular velocity. So from this side we can say I plus m r square into omega. So we have collected omega on one side. So the correct answer is very simple now. Omega equal to m v r by I plus m r square. So that is the angular velocity of the merry-go-round and the kid. So the correct answer is A, m v r by m r square plus I is the correct answer.